All right, here we are. Let's begin. So we've got 3 of these 5 webinars in the can. As Tyler just mentioned last week, we didn't really get all the registrants, so make sure you're registered so you can get the CEUs for last week. This week, I think we're back in the saddle. We should be fine. Today, I'm talking about phosphorus removal. Nick Willis, my partner in these webinars, is away this week. I think he's visiting treatment plants out of state, doing a nutrient optimization out of state, but I'm not sure. We'll find out next week.
Yeah, he's in Iowa.
Oh, okay, that's what I thought. I've been doing some work there, and I thought that he was heading that way. So next week, Nick will rejoin, and we'll do a wrap up for the whole series. And the whole series is all about optimizing nitrogen and phosphorus removal in your treatment plant. And it's been great attendance. Really appreciate all of you signing in. I wanted to repeat this, put these 2 slides in that Nick had up last week because we didn't record this part of it. But I thought it was really interesting and very important. Typos notwithstanding in the graph there. The vast majority of electrical use in a wastewater treatment plant, an activated sludge treatment plant, is aeration, that big blue bar over there, somewhere between 60 and 70%, over half of the electrical use. And very interestingly, to dial in nitrogen and phosphorus more often than not, and I would say the vast majority of the time, ends up with less electrical use. So not only are we talking opportunities for improving nitrogen and phosphorus, we're talking about opportunities for reducing electrical use. And then Nick inserted the second pie chart. This one has aeration a little lower percent, so I guess a couple of different data sources, different analysis, but still over 50% of the electrical use was aeration. And this surprised me, frankly, see how much energy use goes into anaerobic digestion to heat the digesters. The rest of them, not so much surprising, interesting numbers to see. But your biggest use, most treatment plants, is aeration. And then pretty close tie between pumping within the plant and anaerobic digestion. So I just wanted to put all that in the recording. There it is, done that. Now I can move on. All right, so my wife had a big milestone birthday a couple years ago. Went to Paris. While we're in Paris, saw museums. And believe it or not, this is a piece of art by a guy named Cy Twombly. I probably mispronounced it. And I just thought it was amazing. So I've been looking for an excuse to use it. But so while I'm contemplating that on the wall, what I want you to do is contemplate phosphorus removal, science and technology. So let's get into that. Phosphorus removal is really, in concept, is quite simple and straightforward, but the details of it get complicated awfully fast. So here we go. The first complication is there's really 2 kinds of phosphorus that we're concerned about as wastewater treatment plant operators. The soluble phosphorus, okay, that which will pass through a filter, and the total phosphorus. Our permits are written on the total phosphorus. Total phosphorus is the soluble phosphorus as well as the non-soluble phosphorus. Okay, so that's pretty easy to understand, I think. But the soluble phosphorus, the overwhelming, there's a number of types of soluble phosphorus, but unless your permit limit is below 0.1, which I don't think anybody's talking about anything like that, the overwhelming percentage of the soluble phosphorus is orthophosphate, 90% of it, 90+%. So we concern ourselves with orthophosphate, which for all practical purposes is the same as soluble phosphorus. And then it, of course, just to complicate things, goes by other names, phosphate, PO4. Sometimes you see some minuses and other things up above to the right of that 4. Up in here, there might be some other numbers, minus, a couple minus signs or -2. But the PO4 is phosphate, which is the same as orthophosphate, which as far as we're concerned is identical to soluble phosphorus. And then sometimes it's referred to as reactive phosphorus. To keep things simple, I'm going to do my very best to use this thing, the PO4, in some of my schematics, and then refer to it as soluble. So the whole objective in phosphorus removal is to convert the soluble phosphorus to make it non-soluble, to make it part of the mixed liquor, part of the TSS, part of the total suspended solids. That's our process control. We want to take a soluble phosphorus, which is up here, or we'll go through a filter, and we want to put it in and with the mixed liquor. And there's 2 ways to do that. It can be done biologically by having the microbes take the phosphorus and put it inside their little cells, concentrate it there. Or chemicals can be added, and the vast majority of the chemical use is either an iron product, ferric or ferrous. Ferric chloride is a common precipitant for phosphorus, or an aluminum product, alum, aluminum sulfate, polyaluminum chloride pack. In either event, whether it goes biological inside the cells or it's precipitated using an iron or aluminum product, or some of the other rare earth metals that are now being used, it becomes part of the mixed liquor, part of the TSS. So phosphorus removal in a wastewater treatment plant is about taking the soluble phosphorus and putting it into the mixed liquor. And then what? Of course, removing the TSS to keep the effluent with as low a TSS and therefore as low a phosphorus as possible. So until the phosphorus is converted from soluble to a particulate, it's going to flow right out of a treatment plant. It'll flow right through the clarifier. It'll flow through a filter. So our concern, our process control, and what you'll hear me talking about, is monitoring that soluble fraction. We're permitted on the total, but our process control is all about understanding how much of it is soluble, and then whatever's in and with the TSS and whatever portion of the TSS goes out as effluent TSS is going to contain some fraction of phosphorus. There's really 3 environments, 3 steps to phosphorus removal. And this is the kind of simple concept part of it that I really want you to wrap your head around. The first step is, I call it make the candy. It's creating volatile fatty acids. The organisms that remove phosphorus biologically, the PAOs, phosphate accumulating organisms, they're very fussy eaters, and they get their energy from volatile fatty acids. Volatile fatty acids are short chain carbon molecules. It's almost methane gas, but not quite. So we want septic conditions that are almost anaerobic digester, but we don't want that last step. So those of you who run anaerobic digesters, or those of you who have taken the ABC exams or prepping for them, you know about the acid alkalinity ratio for anaerobic digesters. Too much acids and it's a sour digester. These are those acids, volatile fatty acids. So we want to create septic conditions, a sour digester, and that creates the food source. Just to beat this to death, without the volatile fatty acids, we're not going to energize the phosphorus removing organisms. My analogy is it's like the panda bears at the National Zoo, or I guess the panda bears I read recently aren't at the National Zoo anymore. The only ones that we have are in Atlanta. But panda bears eat what? Bamboo shoots. No bamboo shoots, no panda bears. No volatile fatty acids. We're not going to get biological phosphorus removal. Okay, step one is make the candy so it happens in septic conditions. So that means if you receive septage pump outs from septic tanks, every pump out has a lot of volatile fatty acids. So that brings us to the second step, is getting those volatile fatty acids to the right place. And that's a lot of what the technology is about, is to make sure the volatile fatty acids that are produced become available to and are consumed by the right organisms. So the BioP bugs, I may refer to the PAOs, phosphate accumulating organisms, as BioP bugs, because I like that phrase better, but I don't mean to confuse you. But also in septic conditions, given the right septic conditions and the lack of interference from nitrate removing organisms, which I'll dive into later. Also in similar septic conditions as this step one up here, step two, if you bring some of the mixed liquor that's rich in the phosphorus removing organisms, they will consume the volatile fatty acids. As they do, they don't grow. They're just getting energized. It's like this old geezer sitting here and getting fatter and fatter, but they fatten up on the volatile fatty acids. And through a crazy little quirk of nature, this later becomes a great process control tool. They actually reduce phosphorus as soluble phosphorus, as orthophosphate, back into the water. So you can measure how effective these first two steps are by monitoring with the phosphorus, soluble phosphorus, the orthophosphate, going into these vessels and coming out. And if you get the right ratio of increase, actually increasing the amount of phosphorus, then it tells you have a great environment. Third, once they're energized, now we want them to grow. And this happens in aerobic conditions. So it's in the aeration tank. So as they grow, when the conditions are optimal, we've got a good population of the PAOs, the BioP bugs. We've energized them, and we have strongly aerobic conditions, and the pH is above 6.8. That is like a light switch number. If the pH drops down to 6.75, biological phosphorus removal stops. If it drops down for a day, that day you're not getting biological phosphorus removal. Comes back, then the next day you will. If it drops down there too long, you're going to kill off the organisms. You got to start all over. Give them enough air. They're going to take the soluble phosphorus that was in the influent. They're going to take the soluble phosphorus they released back here in step 2, and they're going to bring that into their cells as they multiply. So you end up with more organisms after the aeration, and each organism has a very high concentration of phosphorus in its body, and then the phosphorus is removed as waste sludge. I could put a step 4 in here, which is don't let them re-release the phosphorus, because that becomes one of the nuances of phosphorus removal. Is it's sometimes to oftentimes possible to get through all 3 of these steps, and particularly in warmer water, if you let the solids settle out after aeration. Okay, prior to aeration, I'm going to talk about tools for allowing solids to settle out on purpose. But after aeration, after we've energized and gotten the organisms to concentrate phosphorus in their body, if they settle out too long in warm water, they can re-release the phosphorus. Okay, so I got a question here is, how long should it take to reestablish the bugs? In warmer weather, the phosphorus removing organisms will grow back, I guess in any weather, but more so in the warmer weather, and they're slow. So it can take weeks to a month and a half if you lose your phosphorus removing population. They're like the slowest growing organisms that we're really trying to manipulate in our treatment plants. The ammonia removing are next slowest, and the BOD, of course, are multiplying by the minute. So it can take a fair while for the population to build up the first time, and if you lose it, to bring it back. Hopefully that answers that. If not, keep sending me notes out there. Thank you. Any other questions or comments on that? If so, just type them in. I'm keeping an eye on the comments the best I can, and we'll attempt to respond to anything you have. Okay, so we're going to want a toolkit, because we're going to create some environments and manage what's going on in those environments. And this is going to require more work, more process control, more time on process control, more data gathering, and more thinking about the data and discussing the data than perhaps you've been doing. But I will tell you, it's more fun too, for most people. So for phosphorus removal and for nitrogen removal, like last week, and in fact, I don't know, you probably can't see it, but behind me, I just finished a poster on biological nitrogen removal. So it's kind of fun, put that together. But to monitor the environmental conditions for phosphorus removal and nitrogen removal last week, I'm a big fan of the ORP. And so here's a picture of it looks like the Hawk's new ORP probe here and a meter. And I'm going to go through a couple of tools here to use, and then I'll answer the next question that's popped up here. So to monitor what's going on in the environments, remember I talked last week, I think most of you were tuned in, talked about ORP versus dissolved oxygen, maybe even the third time I've said this. So ORP is a great tool for 2 reasons. One, it tells you the difference between the 2 environments in that it measures how the organisms are using the oxygen. So the more that they're breathing free oxygen, dissolved oxygen in an aeration tank, the higher the positive number. So the spin class would have a higher ORP than little activity. Here we are, an operator at the sleeping at the switch. Still be a positive number here because breathing free oxygen, but this number is going to be higher. And then the other big advantage, and it really gets important in phosphorus removal, those first two steps I talked about happen in zero oxygen environments. So a DO meter doesn't tell you how far into that environment you are, whereas an ORP will not only tell you how hard organisms are working to breathe free oxygen, it'll tell you how hard they're working to breathe the oxygen that's connected to some other molecule. And that's important because we want them to be breaking down the right molecules. So we need it ever more septic for our phosphorus, more septic for phosphorus for the VFA production than we need for the nitrate production last week that I talked about. And the best way to monitor the environment is with an ORP. So let me go through that. I can't remember what I have for my next slide here. Okay, so the first two steps happen in septic condition. The $10 way of saying septic is fermentation. It's kind of nice that this chart I stole from YSI uses anaerobic up here at the top. It doesn't call this an anaerobic condition. To go truly anaerobic, we're moving even more negative. That's your anaerobic digester. So we want to create, I like the target of minus 200. That's a nice, I found that to be a pretty good number for folks to set as an initial target when they're trying to create septic enough conditions to create the volatile fatty acids, the candy that the BioP bugs eat, and to create the environment for these PAOs, the BioP bugs, to become energized by eating the candy. So the DO stops at 0. So with the dissolved oxygen, you can get down to about this 0 number, but you don't know how far over here you are. Then in the second environment, once we've energized them, we want the phosphorus uptake. That means pulling the soluble phosphorus out of the water column and the cells put it inside their bodies. That's the P uptake, the phosphorus uptake. And look at that. If you have aerobic enough conditions to remove ammonia, nitrification, you have aerobic conditions enough to remove phosphorus. So back to that, I really like daily monitoring, field monitoring. I want the numbers today for ammonia at the plant. So if you're doing in-house ammonia testing of the effluent and you're seeing low ammonia numbers, the only way you're getting there is by getting the BOD out of the way to get ammonia removal and creating an environment that's also good enough to support phosphorus removal, with a couple of exceptions, a couple of nuances. And I'll drive those home here during the course of this discussion. But they are making sure the pH can get good ammonia removal at a slightly lower pH than phosphorus removal. So the magic number is 6.8. Like to see it at 7. If you have a pH of 7 in your aeration tank all the time, and you're getting ammonia removal, you've got a good environment for phosphorus removal. Sometimes in some plants, it seems to me, and this is a Grant Weaver observation, a Grant Weaver theory, I don't think you'll find it anywhere else, so consider that when you pursue this next thing I'm about to say. But I've found that in some treatment plants that have a lot of anoxic and anaerobic zones ahead of the aeration, they can chew up so much BOD that there just isn't enough BOD to grow these energized organisms. So that's something I'll talk about at the very end of my presentation today. So there's a possibility that you can get good ammonia removal, because ammonia removal actually not only does not require BOD removal, but it kicks in after the BOD removal is well on its way. So you need a slightly higher pH than you have for ammonia removal. And in summer months, if all the conditions look good, but you're not getting the good phosphorus uptake and aeration, it could be you need to slip some BOD into the aeration. And we'll talk about strategies for that. Okay, so the question was, what do they look like under the microscope? I don't know. I'm sorry. I really don't know. I don't know. I can turn you on to a great resource, is Michael Girardi. Let me type his name in here. Michael Girardi, I think he goes by Michael H. Girardi, has written like a dozen books on activated sludge, and he's a microbiologist. So he's my go-to guy for questions like that. You can probably, and no doubt in one of those books, tells you the right staining techniques and what have you to look for the PAOs. And if not, email me and I'll get you Michael's, he goes by Michael, his email address, and you can reach out to him for more information. All right, so the tools, we're still in the tools section. The tools, there was two categories of tools, and I like to look at it this way. Hopefully it makes sense to you. One is the environments, the habitats. What are the conditions inside the tank? And what are the right conditions, and how do you monitor and control them? And then, of course, there's the monitoring the performance, what happened in the tank. So, for example, if you're monitoring inside the tank, we got dissolved oxygen, we got pH, we got MLSS, we've got ORP. To monitor the performance, we're going to find out what the phosphorus is before and after the tank, what the nitrates are before and after. That's how we monitor the performance of the tank. The very best way, and I love these instruments, they're expensive. They're quite expensive. They can be six figures, $100,000 to get an auto analyzer inline. But some of these inline instruments will measure multiple parameters from multiple locations and track and chart it all for you. I saw one in Virginia that takes samples from 4 locations and does soluble phosphorus, the orthophosphate, does nitrate, does alkalinity, does ammonia. I forgot what else it does, and tracks all that. Great tool. As the numbers get more restrictive, $100,000 investment actually looks pretty attractive. And then the next best is a benchtop spectrophotometer. These are in the $5,000 or $6,000 range for the better ones. Gives you very quick results, 10-minute results for the soluble phosphorus. Again, I'm interested for process control in the soluble phosphorus, so I don't bother cooking the samples to break down to get total phosphorus. I want the soluble phosphorus that goes through the plant. These instruments are so accurate that some of the tests are EPA approved. For the budget, there's a couple of these really nice photometers that are, I forgot, $500-600 a piece, maybe even less. I can't remember. the Hannah brand, they come at a low range and a high range for phosphorus, but you can get the orthophosphate. You can see the phosphate number here, and a much more affordable. The key to me is getting data today and using the data today. The data for reporting, of course, needs to be more accurate. And I'm a big fan of letting commercial labs do that, and then have my lab and my operators integrate with that lab to get the here and now process control data. All right, before I get into technology, any questions on that? There was a question about if the pH is less than 6.8, how long will the bugs survive, or the PAOs, the phosphorus removing organisms? Now, I got to say, I don't know the exact answer to that, but I can tell you that if it drops less than 6.8, while it's below 6.8, they're not removing phosphorus. I also can tell you that if it's below 6.8 for one day and then gets back up the next day, you're going to be fine. It'll jump right back into action. I think it might take as long as a week to kill them off, if you will, but I don't know that exact number. And I really don't know that I want anybody to test it and find out, but if you know. Questions on recommendations on ORP probes. Okay, we're not doing commercials here, but I'm a big fan of the Hawk ORP. It's a really nice instrument. I'm interested in the Hannah. I think I haven't tried them enough to see the reliability. I've had some reliability issues with some of the other instruments. Unfortunately, Hawk is kind of the big name and they have the bigger price and the lousier customer service, but I do like their ORP probe. Nice feature about their devices. You can also put it on a thumb drive as long as you plug in the probe instead of running it off battery. If you plug it in before you turn it on, and then you can program it to collect data every 15 minutes. It goes on a thumb drive. You can take the thumb drive and flip it right into Excel. And then somebody like me loves Excel. We can make graphs and tables and all of that. There are some very inexpensive ORP probes. One looks, it's about twice the diameter of a pen, but it actually will go in your pocket like a pen. I did buy one once, and it was $150 or something like that, but that might have been 10 years ago. So if you're on a real budget, it's better to have something than nothing. So the more expensive ones can get to $2,000 or more for that Hawk unit I was talking about. Anything else? If not, I'm going to jump into technology. And by technology, what I want to do is let's explore plants that are designed for phosphorus removal. Kind of what's the deal? How are they designed to remove phosphorus? Kind of what goes on where? And then after we do that, what I want to talk about is how do we take whatever mess you have of a treatment plant and manipulate it to create the environments that plants designed for phosphorus have designed in, and manipulate that to optimize phosphorus removal. So that's the plan. There's really two ways to go about this in the design world. One is to focus hardware entirely on the mainstream, where all your wastewater goes through the plant. Another one is to take some side streams and manipulate conditions there, and then bring it back into the mainstream. Hopefully that makes sense. You can either not have any side stream process units for phosphorus removal, or you can have some side stream process units. So I'm going to go with no side streams first, and then we'll get into those that do have side streams. I think it gets a little more expensive in the design. So we'll start with the less of the very expensive designs, and then we get into the even more expensive of the expensive designs for phosphorus removal. So to do this, I'm going to show going from left to right, kind of a conventional treatment plant. Maybe has primary clarifiers with some kind of primary sludge. Maybe does not. I can't remember. Do I have that? No. So it may or may not have primary clarifiers. And frankly, for both nitrogen and phosphorus removal, as long as there's the aeration capacity, going to get better performance without primary clarifiers, because having enough organics, enough BOD to drive nutrient removal is often the limiting factor on a treatment plant's capability. So rather than belabor the pros and cons of primary clarifiers, I think you got my feeling on them. Let's talk about what happens for phosphorus removal in the mainstream. These tanks are typically labeled as anaerobic. Okay, and I don't think this will surprise you, but the microbes living inside have never seen the outside of the tank, and if they did, they couldn't see because they don't have eyes, and if they did, they couldn't understand that it said anaerobic because they don't have brains. So they don't react to what the drawings say or what the side of the tank says. They react to the environment inside. And if you have sufficiently septic conditions, there's going to be a family of bacteria that break down all the junk that comes down the sewer system. They're going to break down a goodly portion of it into these volatile fatty acids, the candy that the phosphorus removing organisms not only like, but they need, because that's the only thing they'll eat. I don't know, there's 6, 8, 10 volatile fatty acids. Vinegar happens to be one of them. So without that, we're not going to get the phosphorus removing organisms. The good news is it ain't that hard to make volatile fatty acids, just need septic conditions with a high BOD. So we've broken down some of the organics coming out of the primary clarifier, and this little schematic, even better, if there's no primary clarifier, we're going to be breaking down volatile fatty organics, BOD, to create volatile fatty acids. In the very same tank, from the mixed liquor coming back, right, the return sludge comes back to this anaerobic tank, and with it comes a population, a percentage of the mixed liquor are the bio-P bugs, the PAOs, the phosphate accumulating organisms. So there they are, they're settling out in the sludge. They're coming back in the return sludge. And as those organisms come back, they become energized. As they become energized, they're consuming the volatile fatty acids. Then these energized critters jerk around, and then they flow into the aeration tank. We haven't grown any yet. We've just energized them. So those are the first two steps: create the volatile fatty acids and energize the organisms that remove phosphorus. As they move in an aeration tank, as long as the aeration tank has that magic 6.8 pH, as long as we're getting good ammonia removal, And as long as there's enough BOD still in the water column to support organic growth, they're going to multiply. We're going to have more PAOs than we did before. As they multiply, they're sucking phosphorus out of solution. It goes into their cells. So now our mixed liquor has a higher percentage of total phosphorus than it did before, because now the soluble is a particulate, right? So it's a total phosphorus. Instead of being maybe 1% phosphorus, textbook value says it can get up to 5. I've seen it about 3.5. It's the highest I've seen it. But the sludge now, the mixed liquor now has a much higher phosphorus concentration, and these PAO organisms have a hugely high concentration of phosphorus inside their bodies. Oops, what happened there? So then the PAOs before they go, that's right. I wanted to do the other thing that happens. So also back in this tank, as the volatile fatty acids are consumed by the PAOs, remember earlier I said that phosphorus is released due to some crazy, I call it inconsistency, some crazy thing of nature. It's all part of the whole Krebs cycle. It's an energy exchange system. So the phosphorus now, the soluble phosphorus that's leaving this tank that's operating just the way we want, it's going to be about 3 times the soluble phosphorus of the primary effluent or raw influent blended with the return sludge. 3 times. If it's only 2 times, not septic enough to get the full energizing that we want. If it's 4 times, it's too septic. We've got anaerobic digestion going on. We've got cells dying and releasing more phosphorus in the solution we want. So there's a window in there of what is the optimal. So there's a process control tool. If we measure the phosphorus leaving this anaerobic tank, entering the aeration tank, and compare it to the phosphorus, soluble phosphorus coming in, soluble and soluble, we're looking for a 3-to-1 ratio. So not only do we send the energized PAOs into the aeration tank, we also sent more phosphate into that tank, orthophosphate, soluble phosphorus, reactive phosphorus. So the PAOs, the energized organisms, now are removing that phosphorus they released, plus the phosphorus that came in the influent and made it into our mainstream treatment plant. So these critters now energized, not energized, they've grown, they've multiplied, they're populated with a high concentration of phosphorus. They go into the clarifier. What happens to them? Well, part of them goes into waste sludge, and that's where your phosphorus leaves the treatment plant. And then, of course, part of them comes back to reseed that anaerobic tank. So this is like the main concept for mainstream phosphorus removal. Creating this environment, which does the first 2 steps of phosphorus removal, creates the candy, the volatile fatty acids, energizes the organism, the bio-P bugs, the PAOs, the phosphate accumulating organisms. Happens here, and then the second tank, we're going to have the growth. And as they grow, they remove whole soluble phosphorus out of solution. And then from this tank until the final effluent, we want as little re-release as possible. Re-release happens more in the summer warm water. So we're going to want a lower sludge blanket in the summer weather. We're going to want to make sure there's no settling in the channels, our UV, our disinfection channel. We don't want any phosphorus to get re-released after we've worked hard to remove it in these two zones. So let me do that again. I'll kind of mix the two symbols up just to go through the whole thing again. So we're creating an environment. This is the most standard, I would call it the budget approach for design, but this ain't cheap if it's designed and built for you, but it's an opportunity maybe for modifying your plant. We'll get to that. So what happens? Create the volatile fatty acids. Create the volatile fatty acids in septic conditions. The organisms in the return sludge, there's a percentage of them that are phosphate accumulating organisms. They become energized. The phosphorus concentration leaving this zone is about 3 times what it is going into the zone. Phosphorus is released. Both the energized organisms and that phosphorus they released flow into the aeration tank. Conditions are right. The organism multiplies, so there's now more of them. As there's more of them, there's less phosphorus in solution, so that PO4 faded away, because when this is dialed in, I mean, the kind of concentration in the aeration tank is like 0.05. I mean, plants that are really dialed in, it gets real close to non-detect soluble phosphorus in the aeration tank. Of course, if you do a total phosphorus, there'd be phosphorus in the mixed liquor, right? But we're concerned about the process control, the soluble fraction. So grab a sample, filter it, let it settle, and just pull the supernatant off. We want to know what the concentration is in the soluble portion. We've energized the critters, we've grown the critters, and they're going to flow into the clarifier, and we're going to waste them out as waste sludge. And then we're going to use some of them, of course, to reseed and to go through this cycle all over again. Any questions or comments on that? All right. Seeing none, hearing none. Having had a short drink here, my orange soda, I'll go on to the next. The organisms that remove nitrates love VFAs. They are their porterhouse steak with the bone in, medium rare, on the rare side, if they're me. They'll eat hamburgers, they'll eat salads, they'll eat quiche and tofu. They'll eat a whole bunch of different things to provide the energy to remove nitrate. The organisms that remove phosphorus, they don't eat any of that stuff. Porterhouse steak or nothing. And the organisms that remove nitrate will outcompete the phosphorus removing organisms for the candy, the volatile fatty acids. So if there's a limited supply of volatile fatty acids and there's nitrates in the wastewater, the organisms that remove the nitrates will outcompete the phosphorus removing organisms. You won't get much phosphorus removal unless you produce an abundance of volatile fatty acids enough to satisfy both. So engineers, having realized this years ago, have come up with some pretty clever design strategies to minimize the impact of the nitrates on phosphorus removal. So staying with the mainstream, let's talk through it. And I'll get to your question here in a moment. Thank you for asking it. Okay, the step one, right? We did this last week. It's probably in the chart behind me, but you probably can't read it. Excuse me. Under aerobic conditions, ammonia is converted to nitrate. And then under anoxic conditions, nitrates are converted to nitrogen gas. For that to happen, they need BOD. You need BOD in low oxygen conditions, because if there's free oxygen, the organisms are not going to have, the organisms that can breathe free oxygen will get to that BOD before the organisms that have to breathe off the nitrate. So we have nitrates get produced when ammonia is removed. For nitrates to go to nitrogen gas and bubble out of the wastewater treatment plant and keep KDHE happy with the low total nitrogen, we need anoxic, low oxygen conditions with a lot of BOD. The favorite BOD for these critters is the same kind of BOD that our phosphorus removing organisms need. Volatile fatty acids. So you can see, and since they are more robust organisms and will outcompete, we've got to keep the nitrate removing organisms away from our volatile fatty acids. I'm going to answer that question about 3-to-1 as I get deeper into this. Okay, I'm actually going to show a profile and where to measure and how to do that. So I will get to that. I'm not going to let it haunt me. So better phosphorus removal by design. So I went through the one strategy where you have the anaerobic zone. I like fermentive zone, septic zone, followed by aeration zone for phosphorus removal. Here's an even better way, and we put in an extra tank. And we put in an extra tank with an internal recycle. So this is a design strategy. All I want for you to do right now is to understand what engineers have done, are doing to design their treatment facilities for optimal phosphorus removal. And then we're going to take that information and apply it to what we have. So in between this anaerobic zone and the aeration zone, in the A2O process, what's that? Anaerobic, anoxic, oxic, anaerobic, anoxic, oxic. There's an anoxic zone with an internal recycle. Okay, what's supposed to happen here is ammonia is converted to nitrate. The nitrates go to the anoxic zone. The nitrates are feeding on whatever BOD is coming out of the anaerobic zone to remove nitrates. So then the nitrates in the return sludge should be quite low. Influent is almost all ammonia, has no nitrates. So the nitrate coming in here should be low, which should then turbocharge the performance in the anaerobic zone because there's little nitrate interference. So that's the strategy. So we take the nitrates that are created in the aeration tank through a pumping system, pumps a lot of flow equal to 1 or 2 or 3 times the flow coming in the front door of the treatment plant. So if it's a 1 MGD plant, 3 MGD are being returned. If it's a 30 MGD plant, 30 to 90 MGD are being returned. If it's a 50,000 gallon per day treatment plant, 50 to 150,000 gallons per day are being returned. And as that return comes back, it's rich in nitrates. Last week, I talked about making sure that this return rate isn't too little or too high. And if the return rate is dialed in properly, you'll maintain a strong anoxic environment, be enough BOD coming out of this anaerobic zone, and the nitrates will be reduced to a minimum so that there's very little nitrates coming in the return sludge. So whatever volatile fatty acids are produced in the anaerobic zone, nitrates won't, nitrate removing, the denitrifiers will not be consuming them. They'll be available for the PAOs, the phosphorus removing organisms. Release the phosphorus, 3-to-1 ratio, what's coming in here versus what's going out here. It's a 3-to-1 ratio. The soluble phosphorus and the energized organisms basically pass through the anoxic zone with little to no change. We still have the phosphorus in solution. The energized PAOs are still there. They haven't grown. And in the aeration tank, the energized bio-P bugs, phosphorus removing organisms multiply, and as they do, they pull the phosphorus out of solution that they released, as well as the phosphorus that was in the influent and passes through these two tanks. Okay, let me go back to that picture and I'll see what we have here for comments. How do you determine the point to test for 3-to-1? Like I said, I'm going to actually show some profiles, but usually your return is somehow going into this flow stream, so you can just grab a sample of this flow that includes the return, and you want the soluble phosphorus on that, so you do not cook your sample. And then you want the flow leaving the anaerobic zone going into the anoxic zone, so you just grab it wherever you can, either leaving that or coming into the anoxic. You don't want the return in that. And you measure the soluble phosphorus, the return, the internal recycle. And you're looking for that 3-to-1 ratio. You can take the sample and settle them and just pull the supernate off. You can actually filter the samples, but whatever you do, do not cook the samples. We're looking for the 3-to-1 ratio of the solubles. In the example, does the primary clarifier remove too much carbon from the system that could be used for PAO growth? Generally, yes. Which is why your speaker here is not a very big fan of primary clarifiers. There's a treatment plant in Connecticut that I've been visiting over the years that has 2 primary clarifiers, and they've been offline for maintenance for about 6 years now. And because they're out of service, there's more BOD coming. That plant does not have an anaerobic zone, has an anoxic zone. And that extra BOD has helped significantly with the nitrogen removal. So nitrogen, if you remember from last week, the textbook number is 5 milligrams per liter of BOD for every milligram per liter of nitrate removed. The typical concentration of nitrate is 20 in a plant that removes ammonia. So 5 times 20 is 100. The ratio needed for textbook number needed for phosphorus removal is 25-to-1. So if your phosphorus is 4, say in the effluent, you need another 100. So you would need, by textbook values, 200 milligrams per liter of BOD coming in right here to support phosphorus removal, nitrate removal, and then you basically have none going into the aeration tank. So the aeration tank would be basically an ammonia removing machine. So yeah, if the BOD coming in the influent was not consistently at 200 and you're removing some in the primary, then you're handicapped. So there's a great catch, and the answer is yes. And that's one of the things. I actually have a little test Next week, I'll remember to put that in. Make a note. I've got a little field test that you can run to see if there's enough BOD to support your nutrient removal. So give me a moment. Just making myself a note. We'll talk through that next week. It was a great comment. Thank you for that. Okay, any other questions or comments? If not, we're going to move to side stream. What do we have here? We have 25 minutes left to go. I think this will carry over into next week, and that's fine. That's why we have next week. So for the plants, this is a Missoula, Montana plant. Missoula, Montana plant, Kalispell, Montana, Bozeman, Montana, all have very sophisticated phosphorus removing, biological phosphorus removing designs. And each of them has something like 12 tanks in a row. I mean, a tremendous number of different environments. But we're going to simplify that as well as side streams. So if we take this example I just had, this one does not show the anoxic tank. We're going to get to that in a second example. So we back up 2 examples. This is like your basic AO design, anaerobic tank, aeration tank for phosphorus removal. Primary fermentation. The primary sludge is also often fermented. So it just septic-like conditions, not quite anaerobic enough to create methane gas, right? Because that destroys our acids and our acid alkalinity ratio. So we want almost septic, or we want septic conditions. The BOD in the primary sludge, this is the plants that are designed to have a side stream fermenter. Will create volatile fatty acids. In these designs, they typically take the supernatant from that, not the solids, the liquid that's rich in volatile fatty acids, and they pump that in. So they have a target for how many VFAs they want to produce, a concentration target, and then based on a flow, they get a ratio of VFAs to incoming phosphorus. And man, I just computed what the ratio was and I forgot. I think it's somewhere in the 2 to 5 range. I'll have to get that for next week. VFA to P ratio. So they come up with a ratio and they feed that as soluble volatile fatty acids. They bring it into the anaerobic tank. And then those volatile fatty acids are going to feed and energize the PAOs, the phosphate accumulating organisms, the BioP bugs, the organisms that remove phosphorus. They're going to energize them. So here they go. The volatile fatty acids come into the anaerobic tank. PAOs are in and with the return sludge. As they become energized, they release phosphorus. Now it's a little more complicated blend we need to get. Now we need to measure the 3 inputs for our 3-to-1 ratio. We want 3 times as much soluble phosphorus exiting as coming in. The soluble phosphorus, along with the energized organisms, flow into the aeration tank. And given the right conditions, they're going to multiply and remove the phosphorus from solution. Pretty nice because now you can manage your VFA input and make sure that you're providing enough of that candy to support energizing the phosphorus removing organisms. However, once again, any nitrates that are in the return sludge are going to interfere and they're going to prefer the volatile fatty acids. So this is why these plants that I just mentioned have so many tanks. They start adding tanks. Okay, let's add a tank. So the fermentation now, we're going to take the volatile fatty acids, and we're not going to let the denitrifiers eat the volatile fatty acids. We're going to let them feed on the BOD that's coming out of the primary clarifier as their energy source. So there'll be less nitrate coming into the anaerobic tank, which means the denitrifying organisms, there's no work for them to do. So the volatile fatty acids that flow into that tank are more available to the phosphorus removing organisms. And then the rest of the story, you know, right? So we want to take a combination of these two flows, and if the soluble phosphorus in those two is about 1/3 of what's coming out, then that tells us that conditions here are perfect for optimal phosphorus removal. The soluble phosphorus, along with the organisms, go in the aeration tank, and phosphorus, soluble phosphorus, is very low. Those plants, those three I mentioned, Missoula, Bozeman, and Kalispell, they all produce an effluent total phosphorus of around 0.3. I think they do have filtration after the clarifier. I think in all three cases, at least, I know at least one of them does. So it's a very effective design strategy, and it takes a lot of process control and a lot of monitoring conditions past the aeration tank to make sure that solids are not settling out and re-releasing. But really great control, typical, consistently low effluent phosphorus. So a couple of rules of thumbs here for what they're worth. Anaerobic tank, 1 or 2 hours, doesn't take a lot of retention time, but that ORP needs to get well into septic conditions. And look at that, there's that 25 times as much BOD, and there's the ortho-P, orthophosphate, soluble phosphorus, PO4 release, reactive phosphorus. And then the aeration tank, if there's enough to remove ammonia and the pH is 6.8 or higher, I like 7, it'll have a really low phosphorus concentration. Any questions you want to put out there, please do. And now for the rest of the time, about almost 20 minutes, I've got 2 things that I want to dive into. And if I get to both of them, great. If I only get to one of them, that's fine too. We'll roll it over to next week. First one is monitoring our plants, finding what often happens in phosphorus removal is you finally get it. Okay, things are working, and then they go south. So let's figure out how we keep track of things, and when things start to go off the rails on us, where did they go off the rails? There are a lot of places that can go off the rails, and we got to find the right one if we're going to fix it. I'll probably wrap today up with that discussion. And then next week, after Nick talks about chemical, I think what we'll do is we'll talk about taking your plant and creating these opportunities, both mainstream and side stream, and where do you look to adjust to dial in that phosphorus removal. So that's the plan for the rest of the morning here. So we're going to use an example, sleuthing out for phosphorus removal. Okay, same picture. This one has the side stream fermenter. This picture does not have the the internal recycle and the anoxic tank. So there's really two things I'm going to look for. If the phosphorus effluent, we're monitoring our effluent phosphorus and we see it's getting worse. So the first thing I want to find out is which of these environments, where's it getting worse? So my first thing is to look at the anaerobic tank. Is it doing the two things I need it to do? Is it creating the volatile fatty acids? Frankly, I can monitor that, but I think the better tool is let's monitor the conditions or the performance. So we monitor the performance by taking a blend of the soluble phosphorus coming in and the soluble phosphorus coming out. And if it's in my window, if it's within that 2 to 4 times coming out, it's 2 to 4 times what it was coming in. Then I know I have a strong, viable, this is not the problem. So the problem is not here. More like there's a couple problems that I want to focus on. Is it the aeration tank? Well, if it's the aeration tank, if ammonia is being removed, right? The final effluent is low in ammonia. Yeah, makes me think it may not be the aeration tank. It's got a positive 150 ORP. Frankly, if the ORP doesn't really matter what the ORP is as long as ammonia is getting removed. But let's check the ORP in here to make sure it's aerobic enough. Is the pH high enough? Boy, that's very possible. Less likely in most of your Kansas plants, except for, I think, the Wichita, Topeka, and Kansas City area plants, maybe Lawrence, I'm not sure. But the pH is typically well over 6.8 for all of you, but I don't care what the effluent pH is for this. I want to know what the pH is in my aeration tank. Okay, I'm trying to sleuth out what happened to my phosphorus. It's not here. Is it here? Well, if I can check all these boxes, well, so far it's not there. If we're seeing this, if you're seeing this increase in effluent phosphorus and the water is warmer, now let's look at this BOD issue. And what I recommend you do is take a sample of mixed liquor coming into the aeration tank, exiting this anaerobic tank, filtering it, doing a soluble BOD. And if that number is low teens, 13, 14, somewhere less than 20 milligrams per liter, maybe you've removed all the BOD here and you've got these energized PAOs, but to grow, they need building blocks, right? The organisms, the cells are made out of components that are in BOD, carbon, nitrogen, oxygen, phosphorus, sulfur, all of these components. And maybe there just isn't enough Tinker Toys to make the cell. So that's a good test to do. Now, if you've got 50 milligrams per liter to say of BOD coming in the aeration tank, and your ammonia is being removed, and you've got plenty of pH, well, then the problem isn't here. The problem most likely then is re-release. Yep, somebody unmuted themselves. I don't know if you did it on purpose
absolutely
or not.
Confused now.
Uh-oh, you're confused? Okay.
Oh, shit.
Yep, you're on. You don't want to be? That's fine. So the re-release, so if the ammonia, the aeration tank, you check all the boxes there, the effluent is still high in phosphorus. What's very likely happening is somewhere after the aeration tank, phosphorus is coming out of the solids and back into solution. And here we go. So now this goes back to that question long ago of how do we measure that? So if this was your plant layout and you're really concerned about phosphorus, once a week, I would like you to be doing a profile. I want to know the soluble phosphorus concentration coming into the plant, coming into that anaerobic zone, exiting the anaerobic zone. That's going to tell us what's going on in here. Exiting the aeration tank, entering the clarifier. There's a facility in Athens, Tennessee, oxidation ditch, that in the summer, right here, his phosphorus is like 0.2. Okay, what's that tell me? That tells me all of this is working. His phosphorus right there is 2.0. Well, he's losing phosphorus in his clarifier. It's coming out of his sludge blanket. And then we go further. After the secondary clarifier, maybe there's phosphorus being released in disinfection, sand filter, distribution boxes, you know, a splitter box going out of the clarifier into the clarifier, channels, spots in the channel. And then also let's monitor the phosphorus in our sludge storage so we know what's coming back as a side stream. More likely, frankly, back to here, I probably should have put the re-release as the first. More likely, if the phosphorus removal was, you were getting satisfactory phosphorus removal and it started going bad, it could very well be that it was re-release. And then less likely, but also very possible, could be in the aeration tank. These weekly profiles or every other week, enough to give you history so that you know what the conditions are when things are going well at a certain time of year, and compare that to what's happening now. All right, deep breath. So that was an attempt to sleuth out where the phosphorus removal was not performing to our satisfaction when this tank was working. Now we're going to say this tank is not working. It's getting less than 3 times. If it's getting more than 3 times, you got dead crud in there dying and releasing phosphorus. If it's less than 3 times, it's probably the conditions, either the ORP or the BOD is problematic. And to fix conditions for the ORP is really easy. Is turn off the mixing and allow some solids to settle to the bottom of the tank. And as they settle, in that settled portion, it's going to be much further away from the surface and therefore from the air exchange, because it's a non-aerated tank, and it's more concentrated. So the organisms are going to be breathing any air that might exist to stay alive. So the ORP is going to drop better in that bottom zone. Turn the mixers on again once a day to resuspend, or if you need to do it more often because you see a big drop in your aeration tank mix liquor, obviously you need to turn them on. But the example that I gave when I talked about the case studies of Great Bend turns their mixers on for 15 minutes a day. Otherwise, the solids sit there. And as they sit there, creates a stronger zone for that VFA production, a stronger zone for the PAOs, the bio-P bugs, the phosphorus accumulating organisms that are in the return sludge to settle down into that sludge and become energized from the volatile fatty acids. Second biggest problem is not enough BOD, and those of you listening have caught on to that if there's not enough BOD coming in here, notwithstanding great septic conditions, a nice negative ORP, there's just not enough food, BOD, to break down to create the volatile fatty acids. So in this case, you detune the primary clarifiers. If you have no primary clarifiers and you have a lot of infiltration and inflow during the storm events, you're going to have a problem with phosphorus removal. So you want to sample your effluent for your compliance under normal operating conditions, which would mean not during a storm flow. And that's more representative of your effluent. That's also going to give you better numbers for phosphorus. Hopefully that made sense. I'm sorry to hear the comment. I was confused, but at least you're paying attention. I like that. I don't think I want to run through this. I've got 5 or 6 minutes. I can, but you know what I think I'd rather do is stare at my screen, and hopefully somebody will have a question or a comment, and I can jabber about that. But absent that, maybe I'd go back to that example that I've already probably beat to death of Great Bend and talk about those environments. And now that we've had this discussion, maybe it'll make even more sense what Great Bend is doing. So I'm killing time here, hoping somebody will come in with a comment. Not seeing any. I'm going to run through this and then just scroll through it. And I'm going to start next week, my part of it anyway. I want to do this section. Maybe I'll do a recap of phosphorus and a recap of nitrogen, and then talk about how you can create that in your plant. All right, so we had one comment about nitrification in a Schreiber unit. So let me get back to that. What's the ratio of VFAs needed for 1 milligram per liter if phosphorus? I did calculate that, and I'm going to have to check and get back to you on that answer. Sorry. Okay, so the question about the Schreiber unit is, they have nitrification set. You folks can see the chat as well. So Schreiber unit, I don't have one here ready to bring up, but Schreiber unit's an aeration basin. It's circular. And if this was the aeration basin, it's not in Great Bend, but if it was, the catwalk actually goes around in a circle, and hanging from the bottom of the catwalk are aeration diffusers. And so in the case of Chancey's treatment plant, it maintains a high DO for 75 minutes and a low DO for 70. And of course, during the high DO, as this thing goes around, there's a target. Again, I'm using a clarifier as an example. It maintains a target DO by the blowers coming on and off. During the air on cycle, there's a minimum and maximum DO. It tries to maintain the target. And then during the air off cycle, it's just off. So ammonia removal during the air on cycle, and nitrate removal during the air off. Yeah. So to optimize, there's 2 factors to consider. One is I like to look at hydraulic retention time. So if the plant flow, let's just make it simple. So if the plant flow is 1 million gallons a day, and your Schreiber unit tanks are 1,000,000 gallons, then there's 24 hours hydraulic retention time. If there's 2,000,000 gallons a day and 1,000,000 gallons a tank, the retention time is half a day, 12 hours. So the longer the hydraulic retention time, then it means the longer the wastewater is hanging around, the theoretical drop of water that comes in and then displaces another one before it comes back out again. And it means then you have more flexibility with how long those cycles can be. So at 75 minutes and 70 minutes, what's that? Added together is about 2.5 hours. So if you have 2.5 hours and you have a 24-hour hydraulic retention time, that's almost 10 cycles. 10 times the air's on, 10 times the air is off. You don't need it anywhere near that many times. You can stretch those cycles out if you want to. Stretch either air on or air off, because the wastewater is going to have plenty of time to get aerated for ammonia removal and plenty of time. If you only have 3 or 4 hours hydraulic retention time, those are too long of cycles. So in adjusting it, you want to maintain ammonia removal while improving nitrate removal. And improving nitrate removal means air off cycles, and maintaining ammonia removal means maintaining your air on cycle so you have a positive 150 millivolt. So my guess is you have a lot of room. Yeah, there you go. So you've got 3 days retention time. And you have 3 days retention time, you have a lot of flexibility. You can probably go on and off for 2 or 3 times that many minutes. So make sure you're on long enough to get ammonia removal, and you can stretch your air off times in the winter. Okay, well, when you have those kind of results, you're killing it. And with 3 days retention time, it's understandable why. But now there's a lot of plants. There's a plant in Tennessee that runs 3 hours on, 3 hours off. There's plants that run more than 3 hours on and off per cycle. SBR is the same way. So I think you've got a lot of flexibility. You could probably go as much as 6 hours in this plant. Most plants could not. That's way too long. But I like to see, for most plants, an hour and a half off for the nitrate removal. That's typically a good number to get that nitrate to drop down, or the ORP to become anoxic enough, get down to that minus 100. I think my recommendation, Chancey, would be to target your ORPs. Try to target the ORP during the air off cycle to reach positive 150, maybe keep it there for 15 to 30 minutes. And then that would determine your air on cycle. For your air off cycle, I would target a minus 100. And again, I'd keep it for 15 to 30 minutes at minus 100. Once you reached it, and then I'd go back to air on, figure out how long those cycles are. Or if you got real fancy, you could run it off of inline ammonia and nitrate probes that actually measure when your ammonia removal's good, stop aerating. When your nitrate removal is good, start aerating. All right, those are great questions. Brought us to the end. Next week is the end. And I thank you for listening. If you have any questions or comments at any time, there's my email address. Feel free to reach out to me. Yeah, that's the problem with the trying to keep that equipment from getting tangled up as things go round and round. So there I am. There you are. Thank you very much. Appreciate it. We'll see you next week, I hope. Thank you, and goodbye.